In this video, we'll consider the Weibull distribution. The exponential and gamma distributions are distributions commonly used to describe the variation of non-negative random variables. Temporal non-negative values were described in our discussion of the exponential distribution. Non-temporal quantities arise as well, and examples of these include those shown here: the strength of structural materials, geometric dimensions of solid particles like sand and rocks, the depths of water in a water body, lifetimes of components of a system, physical dimensions of biological organisms, the intensity of the average radiation level in rocks, the amount of rainfall in a given period of time, cost in dollars of floods or industrial accidents. And although the exponential and gamma distributions might provide a reasonable fit to such variables, it's not always as close as desired. And in other cases, the fit may be unsatisfactory. As a result, risk assessors need a family of distributions that's large enough to explain the variability of as many non-negative quantities as possible, while still remaining simple enough in its mathematical form to describe the variability in a non-negative random variable without a lot of parameters. Weibull gave us the Weibull distribution to do this. You're looking at the density function here in the upper left and the cumulative distribution function here. In fact, the Weibull distribution is a three-parameter distribution, but the at-risk version of the function that you're looking at only has two parameters. That would be the alpha and the beta. Otherwise, we have x, which is your data, and e, which is a known constant. Over here, once again, you see a column where we have some data in the x column. I've put in values for alpha and beta, and then using the function, this formula right here is just the density function. I've calculated values that in turn have been plotted here. So if you're inclined, you can change these values, see how it affects the graph. But once again, I remind you that because this is a continuous random variable, these values have no probability interpretation here. As I mentioned, the at-risk version of the function has two parameters. The third parameter is usually called v, and v gives us the smallest possible value of the random variable. So we're going to take a look at risk now. I'm going to go to the defined distributions, and you are going to see when it opens up here, I have enabled the shift parameter. Let me show you where that comes from. When you open a distribution in at risk, you'll usually see this standard line here, and if you click there, it will make a pull down button appear. Click on that pull down button and you see that a shift factor is an option. When I have a shift factor here of 10, this is saying that the smallest value that my variable can take is a 10. Watch what happens when I turn it off. When I turn it off, the distribution shifts back to 0. So when you use the Weibull function in at risk, there is a default assumption that the minimum value is a 0. The Weibull distribution has two parameters, alpha and beta. As you see here, alpha is the shape parameter. It has to be greater than 0. And beta is also a scale parameter. Excuse me, I had to get those tags off. Beta is a scale parameter that affects the amount of the horizontal axis that we cover. Let's take a look at how this works by beginning with the shape parameter. Let's change the shape parameter to a 1. And here you see what looks like the exponential distribution. And in fact, when the shape parameter is equal to 1, the Weibull and the exponential distributions are equivalent to one another. Now let's change that. Let's make it a 2. You notice how the shape has changed. Let's make it a 5. And the shape has changed again. Let's make it a 4. Whoops. Let's make it a 4, and you see the shape continues to shift. So let's leave this as a 4 for the moment. And we'll come on down here to the scale parameter. Notice the horizontal axis now. And the distribution is centered over a 10. Let's add a 0. The shape did not change. But notice where we're centered now. We're centered over 100. Let's add another 0. The shape did not change, but we are now covering much more of the horizontal axis. So the alpha parameter is a shape parameter, and the beta parameter is a scale parameter. The Weibull distribution is a continuous distribution whose shape and scale vary a great deal depending on the values entered for alpha and beta. Now let me close this now, and I want to go to another tab where we're going to talk a little bit more about the Weibull distribution. This distribution is often used as a distribution of time to first occurrence for continuous time processes, much as the exponential is. But there's a difference here. This is one that you would use where there is a non-constant intensity of occurrence of this failure or event or process. This distribution is flexible enough to allow an implicit assumption of constant, increasing, or decreasing intensity according to the choice of its alpha parameter. For example, over here on the far left, alpha less than 1, notice this in this formulation it's 0.4. Alpha less than 1 is used to represent processes of increasing intensity. Alpha equal to 1 is used for constant intensity situations, and alpha greater than 1, in this case a 3, alpha greater than 1 represents decreasing intensity. So let's scroll down so you can see a little summary. A decreasing failure rate would suggest infant mortality or a burn-in phenomenon. That is, defective items fail early, and then the failure rate decreases over time as the defective items fall out of the population. In the center, we have a constant failure rate that suggests that items are failing from random events that are constant in intensity. And then on the far left, an increasing failure rate suggests wear out. Parts are more likely to fail as time goes on. As I mentioned, when alpha equals 1, the constant intensity process is the same as an exponential distribution. The Weibull is very valuable because it gives you, as a risk assessor, the option to choose alpha less than 1 to represent that the older something is, the more likely it is to fail in maintenance or life cycle modeling, or you could use an alpha greater than 1 to represent a decreasing failure rate.